specifically the Schrödinger equation. You guys sent in a ton of material on this. Wow. Textbook chapters, research papers. Clearly, you're ready to tackle this thing.
And you've come to the right place. We'll break it all down. You'll understand not just the basics, but also why it matters so much for, well, for how the universe works at the smallest level.
Okay, so let's start simple. Like, what even is the Schrödinger equation? I mean, what does it actually do?
Basically, it's a math equation. It describes how tiny particles behave, like electrons or atoms. It turns out the world at that level is, well, it's super strange. The rules we use for everyday objects, they just don't apply.
So it's like trying to use a city map to navigate a jungle. Totally different.
Exactly. Schrödinger's equation, it's like our map for this quantum jungle. And one of the craziest things it tells us is, well, it doesn't say exactly where a particle is. It tells us where it might be.
Hold on. So it's all about probability. Like a particle could be in multiple places at once.
Yep. It's a total shift from the way we usually think about physics. The Schrödinger equation, it gives us probabilities, not certainties. And this is represented by something called the wave function.
Okay, I'm seeing this symbol, say, a lot in this material. Is that the wave function?
That's it. Think of, say, the wave function like a map of possibilities for the particle. It describes the state of our system. And when you square it, that gives you the probability density of finding our particle at any given spot.
So instead of a dot on the map saying the particle's here, we have this like blurry cloud showing us where it's most likely to be.
Exactly, a blurry cloud that changes over time.
Which brings us to something else I saw a lot, the time-dependent and time-independent Schrödinger equation. Can you break that down for us without making our heads explode?
Sure. It sounds complicated, but it's pretty intuitive. So the time-dependent equation, we use that when our quantum system is, well, changing over time. Picture an electron moving through a magnetic field. That's when you'd use the time-dependent equation.
So if it's moving and shaking, time-dependent equation. Got it. What about time-independent?
Time-independent is for when things are stable, like really useful for understanding energy levels of atoms. That's key to things like why stuff emits different colors of light.
Gotcha. Time-independent for steady systems. But hold on, you just said energy levels of atoms? We got to talk about that.
Absolutely. And one of the big things that Schrödinger equation shows us is that these energy levels, they're quantized.
Quantized. Sounds fancy. What does that even mean?
It means the energy of our system, it can only take on specific values. Think of it like a staircase. You can only stand on the steps, not in between.
So not a smooth spectrum of energy, but like these set levels. That's so weird compared to how we think about energy normally.
Yeah, exactly. This quantization, it comes directly from the fact that particles act like waves, which is what the Schrödinger equation is all about. It's like a cornerstone of quantum mechanics.
Whoa, okay, mind blown already, and we're just getting started. But I'm also seeing in the research that, this isn't just theoretical. Schrödinger's equation has real-world implications.
Oh, absolutely. It's not just some equation physicists play with. It's behind a lot of the tech we use daily.
Okay, now this is where it gets interesting. You mentioned semiconductors. Like the stuff in our computers and phones, they rely on this equation.
Yeah. The way electrons behave in semiconductors, their energy levels, their movement, it's all governed by the Schrödinger equation. And it's crucial for things like lasers, too, which, well, they're used in tons of things, from telecom to medicine.
So from tiny particles to our everyday devices, it's all connected back to this one equation.
That's kind of incredible.
It is, and it goes even further. The Schrödinger equation is pushing forward things like quantum computing.
Now, quantum computing, that's a whole other deep dive waiting to happen. But how can an equation that describes something as small as an atom be used for something as complex as a computer? It comes down to understanding how these tiny quantum systems work and then using that for computation. Things like superposition and entanglement, those quantum principles, they're being used to create totally new types of computing.
So we're taking the weirdness of the quantum world and making technology out of it.
Exactly. And it's just the beginning. There's so much more to explore. Your material even hints at things like Hilbert space and quantum field theory.
Okay, now you're just teasing us. Hilbert space, quantum field theory. It's like every time we peel back a layer of this equation, there's a whole new universe of complexity underneath.
That's the beauty of it. The Schrödinger equation, it's a gateway to some of the biggest mysteries out there. And while we can't go deep into those today, those concepts take the Schrödinger equation and push it even further, leading to some really wild insights.
So we've covered the basics of the Schrödinger equation, from its probabilistic nature to its applications in technology, and even a glimpse of some seriously advanced concepts. But before we get lost in all the quantum weirdness, let's take a minute to recap and make sure we're all on the same page.
Good idea. Let's take a breather and recap before we dive deeper into what all this means.
Okay, my brain is buzzing a little with all this quantum stuff. Quick recap before we go any further, just to make sure we're all on the same wavelength, huh?
Always good. It's easy to get lost down the rabbit hole, so recap never hurts.
So we started with the idea that the Schrödinger equation, it's kind of like the rule book for the quantum world. Like instead of those Newtonian laws, we use this for tiny particles like electrons.
Right. And one of the big takeaways is that it brings in this whole idea of probability. It doesn't tell us exactly where a particle is, just where it's most likely to be.
And that probability map is determined by the wave function, right? That assay symbol we keep seeing. So instead of a solid little particle, we've got this fuzzy cloud of possibility.
Exactly. It's a big change from what we're used to, but that's how it is in the quantum world. We also talked about the two versions of the equation, time-dependent and time-independent. Time-dependent for when things are changing, like an electron moving through a magnetic field, and time-independent for stable systems, like an electron in a stable atom.
Right. Time-dependent for motion, time-independent for steady states. But then we got into quantized energy levels. Still blows my mind.
And it should. It's a core concept that comes out of the Schrödinger equation. Those energy levels, they're like rungs on a ladder. Particles can only exist on those specific levels, not in between. No smooth transitions allowed in the quantum world.
Crazy to think that energy comes in these little packets at that level, but we also learned that it's not just theoretical, right? The Schrödinger equation, it's behind real tech, like the semiconductors in our phones or those lasers they use in medicine.
Oh yeah, absolutely. Amazing how something describing these tiny particles has such a huge impact on our technology, on our lives even.
Okay, recap done. Feeling a little more grounded. There's one thing that's bugging me. We talked about all this cool tech, but what does the equation tell us about reality itself? At the quantum level, I mean. What's the big picture?
That's a really deep question, one that has been bothering physicists and philosophers for ages. But here's what we can say from the Schrödinger equation. At the subatomic level, reality is fundamentally probabilistic. Instead of a universe of fixed things, we have a universe of possibilities, of potential.
So instead of those nice, solid atoms, we have these blurry, maybe particles.
Exactly. They act more like waves spread out over space, and the Schrödinger equation helps us calculate the odds of finding them in certain spots.
And that wave-like behavior, that's where the quantum comes in, right? It's like the universe is saying, hey, things aren't so clear-cut down here.
Exactly. It's what makes the quantum world so unique. Particles can act like both waves and particles, depending on how we look at them.
So reality is fuzzy down there, but what does that mean for US? Like, is everything uncertain? Should I be worried my coffee cup is going to vanish in a puff of quantum weirdness?
No, not quite. While quantum mechanics introduces probability and uncertainty at the tiny scale, these effects tend to average out when we zoom out to our everyday world. It's like flipping a coin. One flip is random, but flip a million, and it's pretty much guaranteed you'll get about half heads and half tails.
So the randomness smooths out as we go bigger, to the world we experience.
Right. The world we see with its seemingly solid objects, it emerges from that quantum fuzziness. But that doesn't mean it has no influence. As we said before, those quantum behaviors are being used in tech we use every day.
Yeah, like those semiconductors and lasers. It's crazy how something so counterintuitive can be so useful. But speaking of counterintuitive, some of this material goes into even weirder interpretations of the Schrödinger equation, like many worlds and parallel universes.
Oh yeah, that's where it gets really mind-bending. The many worlds interpretation, it tries to explain how quantum possibilities turn into the one reality we see. It suggests that every time a quantum measurement happens, the universe splits, creating a branch for each possible outcome.
Hold on, so you're saying there could be a universe where I won the lottery last week and one where I'm, I don't know, a rock star instead of a podcast house?
Exactly. It's a wild idea, and not everyone agrees, but it shows how the Schrödinger equation, with its probabilities, can lead to some really wild possibilities.
Okay, my brain is officially fried. It's exciting and kind of scary to think there could be countless versions of us out there living out all these different paths, but how can physicists even begin to, like, understand that? Can they even test these interpretations, or is it all just speculation?
That's the tricky part. A lot of these interpretations of quantum mechanics, they're hard or maybe even impossible to test directly. But that doesn't mean they're not valuable. They make us think outside the box, question what we think we know about reality.
It's like that saying, the more you learn, the more you realize you don't know. And the Schrödinger equation, it kind of embodies that perfectly.
Absolutely. And that's what's great about science. It's all about constantly discovering, refining our understanding, And the Schrödinger equation has been a big part of that.
Well, this deep dive has definitely lived up to its name. We've covered the basics, the applications, and even some of the crazy implications of the Schrödinger equation. But before we wrap up, there's one more thing I want to touch on. In the material you sent, there was this interesting discussion about how the Schrödinger equation affects our understanding of time itself.
Ah, yes. That's an aspect that often gets overlooked in discussions about quantum mechanics. The typical Schrödinger equation, it treats time as something continuous and absolute. But some interpretations of quantum mechanics suggest that time might be way more complicated than we think.
Wait, are you saying time might be different in the quantum world? Like, not just ticking away at a normal rate?
Exactly. Some interpretations suggest time could be nonlinear, maybe even branching or looping back on itself. This connects back to those ideas of parallel universes and the many-world interpretation. If reality is always splitting into different possibilities, maybe our idea of a single timeline also needs to be rethought.
Okay, whoa. That's like Inception-level mind-bending. So are you saying time travel could be possible? At least in the quantum world?
It's definitely a possibility that some physicists are looking into. What the Schrödinger equation means for our understanding of time is still being debated and researched. But it shows how powerful this equation is, that it can lead to such profound questions about reality itself.
Well, I think I need to sit down after all that. This deep dive has been incredible, a real journey into quantum mechanics, and I feel like we've only scratched the surface.
And that's the exciting part. So much more to explore and discover. The Schrödinger equation, even though it seems abstract, has opened up so many possibilities. It makes us rethink everything we thought we knew about the universe.
Before we get completely lost in the quantum foam, let's give our listeners some key takeaways.
Great idea. Let's distill all this information into something a little easier to grasp.
So how do we even wrap our head around all this? I mean, we've gone from this equation about tiny particles to, like, probability clouds, parallel universes, even time travel. It's a lot.
It is. And I think the biggest thing to take away here is that the Schrödinger equation, it's precise, yeah, but it also raises more questions than it answers. It really changes how we think about reality itself.
One thing that stuck with me from all this research was how, even though the quantum world is so strange, so different from what we see, it's still the basis for everything. It's like the universe is built on this layer of weirdness.
It really makes you think, doesn't it? All the solid, predictable stuff we experience, it comes from this sea of quantum possibilities.
But how? I mean, if the equation says there are all these possible outcomes, why do we only see one? It's like the universe is making choices, but we don't know how.
That's the question, isn't it? The million-dollar question. And it's why there are so many different interpretations of quantum mechanics. They're all trying to explain how those quantum probabilities become the reality we see.
Yeah, you talked about decoherence, how interacting with the environment makes a quantum system choose a state. But then there's the many worlds thing, where all the possibilities happen just in different universes. Wild stuff.
And there are even more interpretations out there. The material you sent mentioned some, like pilot wave theory, where particles are guided by these unseen waves. It's amazing, Quantum mechanics has been around for a while now, but we're still figuring out what it all means.
It's kind of nice, actually, knowing that even the smartest physicists don't have it all figured out. It makes me feel less bad when my brain melts trying to understand it.
I think that sense of mystery is important. The Schrödinger equation, it doesn't give us all the answers. It's more like it pushes us to keep asking questions, keep exploring.
So even if we don't know exactly how the quantum world becomes our world, we know the Schrödinger equation is a key part of that process.
For sure. And it's not just about theory, the same equation that describes all this weird quantum stuff. It's also helping us build amazing tech. Like quantum computers, for example.
It's like we're taking all that strangeness and turning it into tools that could change, well, pretty much everything. Medicine, materials, it's mind-blowing.
It is. It shows how powerful fundamental research can be. Sometimes the most abstract discoveries lead to the most practical things.
Well, I think it's safe to say this deep dive has been a success. We've explored the Schrödinger equation from top to bottom, and hopefully our listener is now just as fascinated by it as we are.
Totally agree. And if there's one thing I wanted to take away, it's this. The universe is way more strange and amazing than we can imagine. The Schrödinger equation, it's a reminder of that.
Well said. And to our listener, thanks for sending us on this journey into quantum mechanics. We hope you enjoy it.
It's been my pleasure.
And to everyone out there, keep those questions coming, keep exploring, keep diving deep. Until next time, stay curious.